The potential energy of a spring. The spring force is an example of a variable force which is conservative. Figure shows a block attached to a spring and resting on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The spring is light and may be treated as massless. In an ideal spring, the spring force Fs is proportional to x, where x is the displacement of the block from the equilibrium position. The displacement could be either positive or negative, as you can see in figure B and figure C. This force law for the spring is called Hooke's law and is mathematically stated as Fs is equals to minus k into x. The constant k is called the spring constant. Its unit is Newton per meter. The spring is said to be stiff if k is large and soft if k is small. Suppose that we pull the block outwards as in figure B. If extension is xm, the work done by the spring force is Ws is equals to integration limit 0 to xm Fs dx. That one is equals to minus integration limit 0 to xm kx dx. Here Fs is equals to minus kx. After integrating this, we will get the value of work, that is Ws is equals to minus kxm square upon 2. This one is equation number first. Ws is equals to minus kxm square upon 2. This one is equation first. This expression may also be obtained by considering the area of the triangle as in figure D. Note that the work done by the external pulling force capital F is positive. Since it overcomes the spring force, W equals to plus kxm square upon 2. This one is equation number 2. The same is true when the spring is compressed with a displacement xc less than 0. The spring force does work Ws is equals to minus kxc square upon 2, while the external force capital F does work plus kxc square upon 2. If the block is moved from an initial displacement xi to a final displacement xf, the work done by the spring force Ws is equals to minus integration limit xi to xf kx dx. After integration of this quantity, we will get work Ws is equals to kxi square upon 2 minus kxf square upon 2. This one is equation number 3. Thus, the work done by the spring force depends only on the endpoints. Specifically, if the block is pulled from the xi and allowed to return to xi, then work Ws will be equals to minus integration limit xi to xi kx dx, that will be equals to kxi square upon 2 minus kxi square upon 2, that will be equals to 0. The work done by the spring force in a cyclic process is 0. It demonstrated that the spring force, first point, is position dependent only as first stated by Hooke's Fs is equals to minus kx. Second, does work which only depends on the initial and final positions, like equation number 3. Thus, the spring force is a conservative force. the potential energy U of x of the spring to be 0 when block and spring system is in the equilibrium position. For an extension or compression small x, potential energy is U of x is equals to kx square upon 2. We know that minus du upon dx is equals to minus k into x gives the spring force. If the block of mass small m in figure is extended to xm and released from rest, its total mechanical energy at any arbitrary point small x, where small x lies between minus xm and plus xm, will be given by half kxm square is equals to half kx square plus half mv square. This suggests that the speed and the kinetic energy will be maximum at the equilibrium position x is equals to 0. That is, half mvm square is equals to half kxm square, where Vm is the maximum speed, or Vm is equals to under root of k upon m into xm. The kinetic energy gets converted to potential energy and vice versa. However, the total mechanical energy remains constant. In this graph, we mentioned relation between potential and kinetic energy with total energy.